At this point, we've introduced the idea of the Hessian, and we've also walked through one example of the Hessian. Right? The Hessian is this matrix which contains information about the second derivatives of the second partial derivatives of the function
in
all possible combinations. And it also encodes within that matrix, encodes information about what the principal axes of the function are around that point, and also about what the curvature of the function is around that point. And with the Hessian sort of in our toolbox, we can now actually go back and make some connections between one-dimensional and multi-dimensional problems. So let's go back to the one-dimensional case, right? And we identified what the rules were for maxes and mins, and we also identified a sort of approximation approach for one-dimensional functions. So let's first go to an approximation approach for multi-dimensional functions. So if we've got some function that depends on multiple variables, right? So it's a vector function. I'm going to give myself some more room here. So just like in a single variable function, our first approximation for that about some point is going to be that it's the actual value of the function at the point that we're expanding around, right? Our next term is going to be the gradient of the function evaluated at x0 times x, and this will be a dot product, so I probably should do x transpose here. Is that right? Yeah. Okay. And my next term is going to look like the Hessian, right? It's going to look a lot like this 1/2 df squared by dx squared. So it'll be 1/2, and then x transpose times the Hessian times x, where the Hessian is again evaluated at x0. Right? And of course, you will have additional higher order terms here as well, but just as in the one-dimensional case, you're expanding the function about some point, and you've got the term that depends on the first derivative, a term that depends on the second derivative. When you've got a multi-dimensional function, you need to take into account all of those possible derivatives, and that's why you need to use this Hessian matrix. And this then leads us back from the sort of world of approximation up to the world of asking the question, what are the rules for maxes and mins? Right? And so the rules for maxes and mins here in the multi-dimensional case are, first of all, that it is the case that the gradient of the function has to be 0. Right? This is necessary but not sufficient. And it's also the case that if you've got a Hessian matrix, right, the Hessian matrix could be positive definite, right, which means all of the eigenvalues are positive, right? If all the eigenvalues are positive, what does that tell you?
That tells you that your curvature is upwards in all the possible.
Right, so your curvature is upwards in all possible, in all the sort of principal directions.
Right.
Since the curvature is upwards in all possible directions, this corresponds to being at a minimum, right? So just like in the one-dimensional case, when you're at the bottom of a parabola, the curvature is positive. This is sort of the analogous case, but it's analogous in n dimensions, right? It could also be negative definite.
Which just means all the eigenvalues are negative.
So all the eigenvalues are less than 0, right? In which case you're at a maximum. And it could also be neither positive definite nor negative definite, right? So in which case you could also not know, right?
Just like in this case in single variable.
Yeah, just like in this case with a single variable, you could end up not knowing. So you could be at a saddle point. And there are certainly cases where, say, you've got one positive eigenvalue and one negative eigenvalue. That tells you you're at a saddle point. But you could also have the case where, say, the Hessian has a 0 eigenvalue, at which point something else would be going on there.
Right.
So just like in the sort of one-dimensional case, there are rules in multi-dimensions that allow you to assess whether or not you're at a max or a min. Those rules, break down sometimes because those rules are based on an approximation. And just as in the one-dimensional case, there's a sort of handy way to approximate the function about some point that takes into account what the value of the function is, what its first derivative is, and what its second derivative is.